So this is the second in a series of videos providing some background that needs to be in place before we can really talk effectively about scientific reasoning. In the first video in this series, we talked about what theories are, what observations are, what confirmation and disconfirmation are, what experiments are. And here we're going to talk about probability. Now, probability is obviously an important part of science because often what we do when we're doing science is we assign probabilities to theories. So we say, theory A is more probable than theory B, or we say it's a 90% chance that theory A is true, or something along those lines. There's some important ideas related to probability, some important ways of thinking about science, quite general ways of thinking about science that are related to probability, that I want you to have firmly in place before we begin talking about how scientific reasoning works. So let's start with the first and foremost one, and that is this, that there is no certainty in science. Science does not aim at establishing certainty. So why is that? Well, science begins with observation. Now, you might think of mathematics as not beginning with observation, and you might think of mathematics as a branch of science. That's fine. If you think of things that way, I'm just going to say we're not talking about that particular branch of science. We're talking about the other branches of science. That is, we're setting aside math and logic, and we're talking about the rest of science. And that's a rather natural way to think. We think of science as looking at the world, seeing what it's like, or hearing the world. I'm not privileging vision, hearing the world, feeling the world, whatever. Seeing what it's like, hearing what it's like, and then coming to understand it based on having looked at it and heard it and so on and so forth. So you observe the world, and that provides the beginning for scientific theorizing, the initial input. So you can think of that as a way of observing as like measuring the world. And the first lesson here is that observational error, or measurement error, is always possible. So why is measurement error always possible? Well, one reason is that perceptual error is always possible. That is, the world might look a certain way to you, but not actually be that way. It might sound a certain way to you, but not actually be that way. And one reason why perceptual error is always possible is related to how our perceptual system actually works. So let's look at some examples here to illustrate how our perceptual system actually works. So this is a depiction of an eyeball, or part of an eyeball. This little red patch here is the retina. It's light falling on the retina that determines what you see. The eyeball kind of dances around, so the retina gets lots of different light falling on it from, second to second. But let's take a snapshot where on the retina is falling this pattern of light. So this kind of image is striking the retina. That is, there is an object in the world that looks like this, reflecting light, and that light is falling on the retina. Okay? Now, the first thing I want you to see is this. The light falling on the retina here is consistent with two very different ways the world could be. It could be that this pattern, this pattern of light, is occupying most of the retina because there's a small figure out there that's very close to the eyeball. Or it could be that this light, this pattern of light, is occupying most of the retina because there's a gigantic figure out there that's pretty far away. So to see the basic idea here, take your hand and hold your hand kind of close to your eyes, and you'll see that it occupies most of your visual field. That's because it's what's reflecting the light that's mostly occupying the space on your retinas. Now move your hand farther away, and it occupies a much smaller portion of your visual field. So it's making a much smaller pattern on your retinas. The light it's reflecting is making a much smaller pattern on your retinas. But that's not because your hand has shrunk, it's just because it's further away. But notice that a gigantic hand, like a big foam hand or something, that's 2 feet, 3 feet from your body, could occupy the same amount of space on your retinas as your ordinary hand does when it's 6 inches away. So here's the key thing. Both the distance an object is from your eyes and the size of the object determine the size of the patterns it makes on your retina. There's two factors that contribute to the size of the patterns it makes on your retina. Now, why is this relevant? Well, let's look at a little example here. We have two figures, Yao Ming and Larry Bird, and they're in what's called an Ames room, not named for Ames, but named for the creator of the room, a guy named Albert Ames. And you see, it looks like Larry Bird shrinks when he goes to the corner. Right now, he looks way smaller than Yao Ming. And he is smaller than Yao Ming, but when we bring him back to the front, you can see he's not as much smaller as he looked when he was in the corner, right? When he was in the corner, he appeared to shrink. And we can stick Yao in the corner, and you'll see, Yao is quite a bit bigger than Larry, but when he goes to that back corner, he appears to shrink. He appears to be roughly the same size. The question is, why is this happening? Why is it that Yao appears to shrink when he goes to the corner? Why is it the right corner, that is? And why is it that Larry appears to shrink? Why does Yao appear to grow as he moves along the back wall? And the answer is this. Your brain can't determine how big an object is just by checking the size of the pattern it makes on your retina. After all, the size of the pattern it makes on your retina is determined by two factors. It's determined by both the size of the object and the distance the object is from your eyeball. So your brain can't say, the light reflected by that object occupies most of my retina, so it must be really big, because it could be a small object that's just close by. So your brain has to use all sorts of clues to figure out the size of an object based on the size of the pattern it's making on your retina. And those clues amount to guesswork. And that guesswork often does you well. It often leads you to see objects as the size that they are. But especially when the environment is a little unusual, that kind of guesswork, those clues are misleading. They point in the wrong direction. So your brain will end up thinking an object is, say, smaller than it is. That happens in this case because if we think about this room, this wall here is actually super far away from the camera compared to this part of the wall. The wall is on an extreme angle, making this part much closer than this part. So this wall here, this side of the wall, looks a little bit taller than this side of the wall. But in fact, this side of the wall is way taller than this side of the wall. It's just also much, much farther away. And the image this back wall is making on your retina is consistent with two very different ways the world could be. It's consistent with this side of the wall being a little bit shorter than this side of the wall and the two sides being about the same distance from your, the camera. It's also consistent with this side of the wall being way, way shorter than this side, but the right side being much farther away. And based on the pattern of light striking your eyes, based on the image the wall makes on your retina, there's no way for your brain to tell, at least not based just on that. Your brain needs to use various clues. What clues does it use? Well, in this case, it uses clues about the nature of rooms. Rooms are typically such that the walls have approximately 90-degree angles, right? They meet at approximately 90-degree angles. Rooms are typically such that the walls are roughly rectangular and not radically trapezoidal. Same thing with the windows. So this side of the window is actually much longer than this side. It's just farther away from the camera because the wall, again, is on an extreme angle receding away from you. So your brain's like, look, windows are pretty much square or rectangular. They're not trapezoidal. So your brain's like, okay, the image of the light striking my eyes is consistent with this being trapezoidal, with this side being farther away than this side. It's also consistent with the window being square, with the two sides equidistant from me. So I'm going to say it's square because that's how windows usually are. And your brain has to use clues like that because the size of the pattern the window makes on your retina alone is consistent with either way the world could be, either a rectangular or a trapezoidal window. And more generally, the room is designed so that the pattern of light striking your eyes is consistent with a roughly rectangular room with normal shaped floor tiles and doors and, pictures and so on, or a very different kind of room where this wall is sloped radically away from you and is much farther than this side of the wall. Well, your brain settles on the roughly rectangular room because that's how things usually are. Windows are usually roughly square, picture frames are usually roughly square, doors are usually roughly rectangular, floor tiles are usually roughly square, and so on and so forth. And since it settles on that hypothesis, it decides that this wall and this wall are about the same distance from you, even though it happens to be false, right? This wall is much farther away. So suppose your brain has settled on this wall and this wall are about the same distance from you. This side of the wall and this side of the wall are about the same distance. And then as Larry Bird goes to this corner, he gets smaller and smaller and smaller and smaller and smaller. Well, your brain has already decided he's not getting farther and farther and farther and farther away because it's already decided that the two sides of the wall are about the same distance from you. So since the pattern of light he's making on your eyes is getting smaller and smaller, but your brain has decided he's not getting farther and farther away, the best judgment your brain can make is that he must be shrinking. So it makes him look smaller and smaller. Okay, so here's an illustration of the basic point here. We have a door and we ask, is this a rectangle with its handle side closer than its hinges side? Or is it a trapezoid with its handle side and its hinges side the same distance away? Well, our brains naturally interpret it as a rectangle with the handle side and the hinges side at different distances from us. Our brain naturally says, look, this line here is shorter than this line here because, not because this side of the object is longer, not because this is a trapezoid, but rather because this side of the object is closer to our eyes than this side. Why? Because doors are usually rectangular, not trapezoidal. And it says that even though these lines are very different lengths. And it has to make judgments like this. It has to make guesses like this in order to judge size and distance. Because there's nothing about the image striking your retina, the light striking your retina, the image on the retina, that determines size versus distance. Okay, let's look at another example, one involving color. So here we have an object. I'm going to hide the surrounding information, and you can see that the gray down here and the gray down here are the same. When I take away that information and leave the middle blocked out, the grays might look, the top might look a little bit darker, but they look approximately the same. Now I'm going to take away the middle, and you'll see the top goes to looking very dark and the bottom to very light. If you think this is some sort of trick, use your finger to kind of cover up the middle portion. So use your finger to block out your visual input from here, and you'll see that the bottom and top look roughly the same. Well, how can that be? So let's just sit our two images side by side here, and we can think about how this works. So this is a side view of the object. So if we go back here, this is like surface A, surface B, surface C, and surface D. Surface A is up here, surface B is down here, C is in here, and D is down there. So this is a side view of the object. We have a light source, we have an observer. The light from the light source is striking the object. It's being reflected into the person's eyes. Okay. Now the bottom part of the object is in shadow because the light is coming from the top. And because the bottom part is in shadow, the light being reflected from down here is not very bright. It's very indirect light, right? But the top part, A, surface A, is in full sun. So the light being reflected is very bright. So when you look at this object, and the object here is uniformly colored, right? It's all the same color. If you look at this object, which is uniformly colored, with a light source coming from above, which is where light sources usually come from, given its shape, because B is in shadow and A is in full sun, the light striking your eyes from surface A will be very bright, and the light striking your eyes from surface B will be very dark. That means if your brain builds a perceptual experience, a visual experience, if it makes it look, the way it makes it look is determined just by the light striking your eyes, it would look like this. It would look like the top is very bright and the bottom is very dark. But that's wrong, right? The top is not very bright and the bottom is not very dark. So if your brain uses only the light striking your eyes to build the image, then it's going to give you the wrong answer. It's going to say the object is variegated in color, not uniform in color. But in fact, the object is uniform in color. So what does your brain do? Well, your brain knows that the top is in full sunlight and the bottom is in shadow. So it says, look, if the light striking my eyes from surface A is very bright and the light striking my eyes from surface B is not very bright, that's not because A itself is bright and B itself is dark. It's because B is in shadow and A is in full sun. So if the light striking my eyes, here is bright and here is dimmer, that's because it's a uniformly colored object with A in full sun and B in shadow. So it makes you see the object as roughly uniformly colored, which it in fact is. So it gives you the right answer. Okay. Now let's imagine the object in the world itself is different. A is very dark and B is very light. So A is like a dark blackish grayish and B is a kind of lighter gray. And again, A is in full sun and B is in shadow. What's going to happen now? Well, the light coming from surface A and B might be exactly the same, right? A darker object in full sun will reflect bright light, or light of this brightness, and a brighter object in indirect sunlight will reflect light of the same brightness, let's say. So if your brain builds an image based on just light striking your eyes, it's going to say the object is uniformly colored, all dark, but your brain knows better. It knows that A is in full sun and B is in shadow, so it's going to adjust, and it's going to make the object look as it is. It's going to make A look dark and B look lighter because that's how it is in the world. Now, let's think about this in relation to the example we looked at here. When light strikes your eyes from these two surfaces, it's the same color. Why? Because A and B are in fact the same. Okay, they don't look the same to us, but they're the same. So then what does your brain do? Your brain says, well, this is an object being illuminated by light from above, because that's how objects are normally illuminated. Now that's wrong, right? The object is not illuminated by light from above, but your brain has been trained to think that's how it works, right? This is an image projected on this is, an image, pixels coming from a screen. There's no illumination source from above that's determining the colors here. So the light from A and B are the same, but your brain's like, hey, A is in full sun and B is in shadow. So if the light from A and B is the same, that must be because A is in fact darker than B. So it makes A look darker than B. Now, every time you see shade, and more generally, every time you see color, your brain has to go through this kind of procedure because it has to figure out how much of the light striking your eyes is the result of the nature of the object and how much is the result of the nature of the light source. And because it has to go through this process, it has to make guesses. It has to do a variety of guesses. So just like determining size and shape requires your brain doing a bunch of guesswork, determining color, shade, requires your brain doing a bunch of guesswork. Let's look at another example here. This is a little box and a little bit of piece of viewing apparatus. The box is, as you can see, opaque. You can't see into it. Along comes an observer who looks in the box. And what does the observer see? Well, inside the box, there's a little plastic square. So this is not something the observer could see. I'm just showing you what's inside the box. There's a little plastic square, roughly two-dimensional. And the observer has a visual experience as of a little plastic square. At least that's what you'd think. But in fact, this viewing apparatus here skews things. It makes objects look about twice the length they in fact are. So it's going to make it look like that. Okay? So that's the visual experience the subject would have. Now, here's an experiment. In condition 1, the experimenter says, I want you to look in the box. And the observer looks in the box and has a visual experience like the one we just described. And then the experimenter says, which of these templates matches what you see? And the observer is going to pick this one. So the second tallest rectangle, because that matches how it looks to her. Now here's condition 2. We don't have the viewing apparatus anymore, so the subject in the experiment is not going to look inside. Instead, there's a little hole in the bottom, and the experimenter says, I want you to reach in and touch the object, and then says, which of mine matches what you see? Or, sorry, which of mine matches what you feel? And what do you expect the subject to say? Well, it's a rectangle, it's a square in there, and it feels square, so the subject says square, right? She says it feels like a square. And, this is representing her tactile experience, her experience of how it feels. So she says it feels square. None of that's been interesting so far, but here comes the interesting bit. In condition 3, the subject is told to look inside, and then after that, reach inside and feel while still looking. So the subject looks inside, and then after that, reaches inside and feels while still looking, and then is asked to say, which of mine matches what you feel? Okay? Not what you see, not what is the object, but which of mine matches what you feel. Now, the subject is having a visual experience of a certain sort and a tactile experience of a certain sort, and is asked which of which of these templates matches the tactile experience. And the subject says the second tallest rectangle, just like she did when she was asked which of mine matches what you see, but not like she did when she was asked which of mine matches what you feel when she wasn't looking. So why is that? Well, she's having a visual experience like this, and the question is, what is her tactile experience like? The fact that she says the second tallest rectangle matches what I feel suggests that the tactile experience is like this, that somehow the stimulus to the eyes is influencing how it feels to her hands. So here's a way to think about it. In condition 1, which of mine matches what you see is what's asked. You see only and you say rectangle. In condition 2, you're asked which of mine matches what you feel. You touch only and you say square. In condition 3, you're again asked which of mine matches what you feel. you're both seeing and touching, and you say rectangle. And the question is, why? Well, the first two cases, it's easy. You say rectangle in the first condition because it looks like a rectangle. You say square in the second condition because it feels like a square. So why do you say say rectangle for feel in the third condition? Presumably, it's because it feels rectangular. So why think that? Well, first, people don't report any conflict between what they see and what they feel. They don't say, well, it feels square, but I'm going to say rectangle because that's how it looks. Second, and more importantly, there's a kind of fourth condition here, where subjects again are told to look inside and then reach under and say what they feel. So they look inside, then they reach under. They're again asked which of mine matches what you feel. So this is proceeding just like condition 3. They say the second tallest rectangle. But then the experimenter says, now close both eyes. And what do you think is going to happen when subjects close both eyes? Well, often when they close both eyes, they scream or they retract their hand quickly. And when the experimenter says, why did you do that? Why did you scream or why did you retract your hand? Subject says because the object moved. Now the object didn't move. So why does the subject say the object moved? Well, the answer is pretty straightforward. The object felt rectangular to them because the stimulus to their eyes was influencing how it felt to their hands. But it wasn't rectangular, so when they closed their eyes, it went back to feeling square. Well, it can't go from feeling rectangular to feeling square unless it shrinks. So it feels like it shrinks, and it can't feel like it shrinks unless it feels like it moves, so it feels like it moves. So when asked, why did you scream? People say it moved. Okay, so it looks like in condition 3, it feels rectangular even though it's square, and even though when they're not looking, it feels square, which is what it is. The question is why, and the answer is because the stimulus to the eyes influences the processing in the tactile system. This is called a cross-modal effect. There's lots of these kinds of effects, but here I want to just paint a general picture of general picture of perception. So you have some input from the world. This could be light striking your eyes, or mechanical pressure on your skin, or sound waves striking your ears. Your brain then has a bunch of unconscious biases built in, a bunch of implicit biases, a bunch of automatic processing that it does. And then it gives output of some sort of perceptual experience. So you might get an input of a concave face. And then your brain has a bias that says the probability that that an object is convex given that it's a face is way higher than that it's concave given that it's a face. And it will output an experience of a face being convex even though it's concave, as in this case. This is an example we might look at in class. You might get an input of two grays that are the same, but your brain says, well, the probability that these aren't the same given the shading information, given that the light is coming from above and the shading information from the middle of the object, is greater than the probability that they're identical given the shading information. And on the basis of that, it outputs the two surfaces looking different, even though they're in fact the same. Here's another example we'll look at in class. So every time you see, your brain uses unconscious biases to decide what's most probable given the signals from all your sense organs. It then makes things look however it decides they probably are. The same goes for your other senses. These presumptions are based partly on your personal stimulus history. That means things can appear different to different people and appear different to the same person at different times. And here we have the dress, which hopefully now you're in a position to understand. So why does the dress look bluish and blackish to some people, but whitish and goldish to others? Well, the answer is pretty straightforward, and it's related to that two grays example we already looked at. There's light waves striking the dress, okay? And suppose that you're somebody for whom this portion of the dress right here where the cursor is looks blue, and this portion looks like darker, like a blackish. Well, why is that? Well, your brain is saying, look, there's blue light waves striking my eyes coming off of this surface, right? Coming off of right here. And there's two reasons why there might be blue light waves striking my eyes. One could be because the dress disproportionately reflects blue light. That is to say, the dress itself is blue, and there's ordinary white light striking the dress. So ordinary white light, light of all different wavelengths striking the dress, but the blue ones get reflected because the dress is blue, and that's why it looks blue. Another reason, a very different reason why it might, there might be blue light waves striking my eyes, is because this is a white surface, and the light striking it is very blue. When objects are in shadow, the light striking them is bluer, so that would be the reason why, if it were in shadow, the reason why the light striking it is disproportionately blue. So you have a white surface being struck by disproportionately blue light, so it reflects disproportionately blue light. So the reason there's blue light wave striking my eyes is because it's a white surface being struck by blue light. Now your brain has to choose between those two hypotheses. The hypothesis that says it's a blue surface under ordinary white light, and the hypothesis that says it's a white surface under especially blue light. And there's no way it can choose just based on the light striking your eyes. It has to use background information and clues. And here the clues are pretty unclear. It's unclear whether this dress is in direct sunlight or under ordinary white light or instead in shadow. And because the clues are unclear, different people's brains pick different answers. If you see this area is bluish, it's because your brain says, ah, it must be a blue dress under white light. If you see this area is whitish, it's because your brain says, ah, it must be a white dress under blue light. Okay, so perceptual error is always possible because perceiving is your brain making suppositions based on probability. That is, perceiving is your brain making presumptions. It's making its best guesses about how the world is. And because perceptual error is always possible, and observation is just a kind of perception, and it means that, measurement error, observational error is always possible, which means you can't be certain of a scientific claim that's based in observation, which is how we're thinking about scientific claims. They're claims that are based initially in observation. Okay, we'll stop this video there. In the next video, we'll consider another reason why measurement error is always possible, and that's because your sample might be unrepresentative by chance.